In this video, we will practice using the first fundamental theorem of calculus. In previous lessons, we have used this theorem to evaluate definite integrals. And we learned to find the antiderivative, and then we would evaluate at the upper limit of integration, and then we would subtract the value at the lower limit of integration. So this is where we have used the first fundamental theorem of calculus in the past. But now we are preparing to use this theorem to help us solve real-world problems. So we need to switch our perspective a little bit. First of all, the integral of a derivative takes you back to the original function. So instead of talking about the antiderivative, capital F of x, the integral of f prime will just be f. So this same rule becomes f at b minus f at a. If we add f at a to both sides of the equation to get f at b by itself, we end up with this equation. This is just another way of writing the first fundamental theorem of calculus, but this form will be more useful to help us solve word problems. To help us see how we will use this in the context of a real-world problem, let's look at what we see on the left and translate it into words on the right. First, on the left, we see this integral of f prime. F prime is a rate, and then what we get is this difference in amounts. So in general, the integral of a rate will equal the net change in the amount. This last form is so useful because it is already solved for the end value, which is often what we are looking for. So let's examine what we have. We have the end value equals the initial value plus the net change in amount. We just saw above that the integral of the rate is the net change in the amount. Let's practice. Each one of the following statements is false. We need to change the underlined part in order to make the statement true. Notice that we will be using capital letters to represent antiderivatives. For example, capital F will represent the antiderivative of function f. So what's wrong with this first statement? When you take the integral of function f, you need to find the value of the antiderivative at the upper and lower limits of integration, not the derivative. So we need to replace this with capital F at 2 minus capital F at 1, the antiderivatives. Statement B has the same issue as the previous problem. However, this time f of x is underlined. So we need to change this part in order to fix the issue. So what can we do? We know that the integral reverses a derivative. So we need something that if you integrate, it will give you f prime. So that means this has to be f double prime. If you integrate f double prime, you end up with f prime. Let's see, what about statement C? Well, notice that these g's are all at the same level, g, g, g. If we integrate, we need something that will turn into regular g, and that would be g prime. If you integrate g prime, you get g. So what's wrong with statement D? Looking at the function j, we see that they are all on the same level, j, j, and j. When you take the integral of a function, it takes it down a notch. So, for example, you might go from j double prime to j prime, or from j prime to just j. They won't be on the same level. So the integral of what will give you just j? The integral of j prime will give you j. So this will be the correct statement. Well, what is wrong with statement E? This time we have the integral of h prime, and we are ending up with just h. That makes sense, so what's wrong? I think it will help if we rewrite this using words. Remember, when we write the first fundamental theorem of calculus in this form, it means that the end value equals the initial value plus the net change. However, if h at 2 is the end value and h at 5 is the initial value, then this integral is in the wrong order. The limits of integration have to go from the initial value to the end value, and these are backwards. So here is the correct way to write the statement. H at 5 is the initial value. H at 2 is the end value. So we will integrate from 5 to 2. Statement F has a different type of problem. When I compare the left side of the equation to the right side of the equation, I noticed that they took the constant of 2 and they pulled it outside of the integral. There's nothing wrong with that. So what's the problem? Well, there's another change that they made from the left side to the right side. They have reversed the order of the limits of integration. So on the left side, we are integrating from 1 to 3, and then on the right side, it becomes 3 to 1. This is okay, but if you reverse the limits of integration, you have to change the signs. So this would be the correct statement with a negative 2 instead of a positive 2. For this next set of problems, we are given two facts. F prime equals sine of pi x, and f at 2 equals 0. We will use this information to answer the questions. Notice that we will not necessarily need the first fundamental theorem of calculus to answer the questions. Let's start by finding f at 3. I think we can use this new form of the first fundamental theorem of calculus to find f at 3. Let's look at it as the end value equals the initial value plus the net change. So f at 3 will be the end value. Let's treat f at 2 as the initial value. Then the net change in value will be the integral of f prime. We will integrate from 2 to 3 because f at 2 is the initial value and f at 3 is the end value. We know that f at 2 is 0, so I'm making that substitution. Of course, f prime is sine pi x, so there you go. So if I want to find the value of f at 3, I really just need to integrate sine pi x from 2 to 3. Be careful here. The antiderivative of sine is negative cosine, but yet this is not the answer. That's because on the inside, we don't just have x, we have pi x. So technically we need to do u substitution. This is so simple that we should be able to do it mentally. Just ask yourself, what is u and what is u prime? And you really don't need to write this down. The u would be pi x if we were doing u substitution. That means u prime would be pi. When u prime is a constant, we just wind up dividing by that constant. So instead of just getting negative cosine pi x, we're going to get negative 1 over pi, right? We're dividing by u prime. To evaluate this definite integral, we need to find the value at 3 and subtract the value at 2. So here's the value at 3 minus the value at 2. What is the value of the cosine of 3 pi? Well, 3 pi is over here on the left. The cosine is negative 1. So we have a negative 1 right here. What about the cosine of 2 pi? That's positive 1. So we are multiplying by a positive 1 here. Negative 1 over pi times negative 1 is positive 1 over pi. So we have positive 1 over pi minus negative 1 over pi. Minus and negative is addition, so we have 1 over pi plus 1 over pi. But that will be 2 over pi. So that's how you find f at 3. Now we need to find f prime at 3. We are given that f prime of x equals sine of pi x. So f prime at 3 is sine at 3 pi. But sine at 3 pi is 0. So f prime at 3 is 0. Finally, we need to find f double prime at 3. We are given that f prime of x is sine of pi x. So f double prime of x will be the derivative of sine of pi x. We know that the derivative of sine is cosine. So we have cosine pi x. But because this is not just an x inside, we have to do the chain rule and multiply by pi. So f double prime at 3 will equal the cosine of 3 pi times pi. F double prime at 3 will equal, what is the cosine of 3 pi? Well, that's negative 1. So we end up with negative pi. And that's it. We found all three. For part B, we need to find f at 1/2 and f at 0. Let's start with f at 1/2. Using the first fundamental theorem of calculus, we have this. We are given that f at 2 is 0 and f prime is sine of pi x. So now we have this. Taking away the 0, we have this. In part A, we found that the antiderivative of sine of pi x is negative 1 over pi cosine of pi x because of our mental u substitution. So now we have this. To evaluate, we need to find the value at 1/2 and then subtract the value at 2. So here's the value at 1/2 minus the value at 2. But the cosine of pi over 2 is 0. And the cosine of 2 pi is 1. So the value of the first bracket is 0. And in the second bracket, we have negative 1 over pi. But minus a negative is a positive. So this is 1 over pi. So f at 1/2 equals 1 over pi. Now let's find f at 0. The first fundamental theorem of calculus gives us this. Since f at 2 is 0 and f prime is sine of pi x, we now have this. Let's go ahead and get rid of that 0. From previous problems, we know that the antiderivative of sine of pi x is negative 1 over pi cosine of pi x. And because this is a definite integral from 2 to 0, we will evaluate from 2 to 0. We must find the value at 0 minus the value at 2. The cosine of 0 and 2 pi are both 1. So we have negative 1 over pi times 1 minus negative 1 over pi times 1. But that's just negative 1 over pi plus 1 over pi, which equals 0. So f at 0 equals 0. For part C, we need to decide if f of x is increasing, decreasing, or neither at x equals 3/4. First semester, we learned the graphical relationship between f, f prime, and f double prime. Specifically, we learned that f will be increasing when f prime is positive, and f will be decreasing when f prime is negative. We are given that f prime is sine of pi x. So that means f prime at 3/4 will equal the sine of 3 pi over 4. 3 pi over 4 is in the second quadrant, where the sine function is positive. So the sine of 3 pi over 4 is 1 over radical 2, or radical 2 over 2 if you prefer. What matters is that this is greater than 0. So f of x is increasing at x equals 3/4 because f prime at 3/4 is positive. For part D, we must determine whether f of x is concave up concave down, or neither at x equals 3/4. We know that f will be concave up when f double prime is positive, and f will be concave down when f double prime is negative. We are given that f prime is equal to sine of pi x. F double prime will be the derivative of f prime. The derivative of sine is cosine. However, because this is not just an x on the inside, we have to do the chain rule and multiply by the derivative of the inside, which is pi. F double prime at 3/4 will equal the cosine of 3 pi over 4 times pi. The reference angle is pi over 4, and the cosine of pi over 4 is 1 over radical 2. Some of you like to say radical 2 over 2, which is fine. Since 3 pi over 4 is in the second quadrant, the cosine of 3 pi over 4 will be negative 1 over radical 2. And then we have times pi, so I'm going to just put pi in the numerator. All that really matters is that this is negative. F of x is concave down at x equals 3/4 because f double prime at 3/4 is negative.